Hello everyone, this is chapter 9, the part that I would like to talk to you about hypothesis testing and the null hypothesis testing. So this is just going to be the first part of chapter 9 from Spatz. So in the previous chapters 1 through 8, it's been mostly about descriptive statistics. So now we're going to really get into inferential statistics, and we're going to start with our t-tests. But before we get there, let's talk about null hypothesis testing. And so this is going to be what we're going to be focusing on for the rest of the semester here, and how we do our tests. So we're going to be talking about the null. So in chapter 8, we use confidence intervals to give a confidence about what the actual true average was out there based off of sample data. So it's sort of along that same line. So if we're trying to make an inference about what the true population parameter is, we have a confidence interval we calculated from last chapter. And so we're going to do a little bit more when it comes to understanding what we can infer about the population based off sample data. So chapter 9 is going to cover the null hypothesis. We're going to talk about some effect sizes. And then I think in later on, chapter 9, we're going to talk about the first t-test. But we need to understand what the null is now, because it's going to be used in ANOVAs, in factorial ANOVAs, one-way ANOVAs, multiple t-tests, and chi-square. So we need to figure this out now.
So the textbook, Spatz textbook, uses the Doritos example, which I'm going to refer to quite often now. So if you're familiar with the textbook, it basically says a person buys a bag of Doritos. Apparently they're probably still hungry. They look at the bag and they say it's got 269.3 grams in it. And this person is still hungry, saying, I don't believe it. So then what you really need to understand is, how does Frito-Lay know how many grams are in that bag? Did they weigh every single bag? No, they didn't. They don't weigh every single bag in order to make sure. What they did was they took a sample of all those bags and they weighed them, and then they took the average weight. So this particular person is saying, no, I believe that I'm assuming they probably assumed that they underestimated or they overestimated on the bag, so that what's in the bag was underestimating. So what I need you to be familiar with is, right down here we got mu sub 0. So mu sub 0 is the claim of the population. So it's what does, in this example, what does Frito-Lay claim as the population average? What's the mean? Mu sub 1 is the unknown true population. So Frito-Lay is claiming something. They're not 100% accurate on it because, again, they took a sample, and we know samples are inaccurate. So this mu sub 1 is the unknown, the unknown, always unknown, true population mean. So I just need you to be familiar with that nomenclature there. So I'm going to refer to null hypothesis statistical testing, so NHST. So we've got the hypothesis of equality or the hypothesis of difference. So generally we assume equality to begin with. So we assume mu sub 1, the true population average, is equal to what the claim is. Or you can have the hypothesis of difference, that you assume that, no, it's not true. The true population average, mu sub 1, is not equal to mu sub 0. So the null is always included the equal marks. Therefore, the null is always going to be what here? It's always going to be the hypothesis of equality. So the null, we start with this idea that they're equal. So you don't. This is a big kind of idea for you to understand when it comes to research. You typically see something in life and you go, you know what? I don't believe that. I don't. So this Frito-Lay example for this Doritos, the student who purchased the bag was, no, I don't believe this. I don't believe this is the case. They believe the hypothesis of difference. But the real issue is that you don't ever test this directly. You always start with this with null hypothesis testing. You assume that they're equal to begin with. So in order for the student to do any statistical analysis, some null hypothesis statistical testing, is that they have to start with this idea that it's equal. So you start with this idea that they're equal, and then if you find evidence to support or reject this equality. So null hypothesis always is hypothesis of equality. So the null is equality, therefore the alternative hypothesis is typically, the alternative hypothesis is what the researcher is using their alternative hypothesis, is that they're not equal. So that's the hypothesis of difference. This is typically symbolized H sub 1. H sub 0 is typically the null hypothesis. So what are the possibilities of this relationship if they're not equal? So if they're not equal, what can happen? This one could be, if they're not the same, this one could be either what or what of this. This could be either larger or smaller of this. If this one's larger, they're not equal. If this one's smaller, they're not equal. So right now, there's theoretically two possibilities here. Not equal means one could be larger, the other one could be larger. So how do we accept one of these hypotheses? So for this, we need to start by assuming the null is correct. We start assuming that they're equal. I know this is kind of sort of counterintuitive. Again, going back to this research example from this student, this Doritos, they believe that they got gypped. So they believe that it's unequal than what's on the package, but that's not how research logic null hypothesis testing works. It starts assuming that they're equal. So then what happens? You take some samples. Now you have a sampling distribution, which we learned last time from chapter 8 was the t distribution. So we got samples. So again, depending on what our t values are based off of how large our samples are, we've got to use that graph again. I'm sorry, that appendix table. If the probability of the value you found is large, you can accept the null. So what does that mean? The probability of the value you found. We'll talk about this. We'll show you this in the worksheets. But the probability of getting your sample, given everything is the same, everything is equal. If it's large, we accept the null. If the probability of the value you found is small, then you reject the null, saying that they're, so say the two values, then you get to say the two values are different. So again, think back to the sampling distributions we talked about in class. So say the true average shoe size is a 9. Well, you take a sample of 50 Marian students and you get an average of 8.5 from your sample. What's the likelihood of getting a sample of 8.5 if the real population average is 9? Well, it's pretty high. The probability is going to be kind of high. I mean, if it's really 9 and you get pretty close to 9 at 8.5, you're like, oh, that's pretty high. That's fine. But if the true population average, so in this case would be mu sub 0. If mu sub 0 mu sub 1 was 9, but then your sample, you end up getting a sample average of, let's say 6. The odds of getting a sample of 50 Marian students with a shoe size of 6, given that all Marian University students' shoe size are 9, is pretty damn low. And if it's really low, then we get to say, I don't believe 9 anymore. I don't get to trust. So I don't believe that those two averages are equal. So that's what we're talking about with this probability, the probability of getting a sample. And so you probably intuitively think if you get a sample that's sort of close to what you believe is the case, they're probably going to be the same. If you get something that's vastly different, then that probability's got to be kind of low. So we ask ourselves with this question, what value is small enough? All right, well, again, just go back in time, old dead white guys came up with it. So, getting back to the old dead white guys. So we got, who gets to set the alpha? And that's what the alpha is this, how small is small enough to say that we reject? It's widely accepted that the value is 0.05. I wouldn't say it's 100% accepted because there's yahoos online trolling the internet talking about we shouldn't use 0.5, but whatever. For the remainder of this class, it's going to be 0.5. So the probability of alpha equal to or less than 0.05, you get to reject the null. That's what this reject h sub 0 is the null. But if p is less than 0.05, you reject the null. Two values are statistically significantly different. So I've been trying to hold off on this in this particular class. You've probably heard this before. When are you able to use those words in a scholarly research kind of scientific way? Well, it's here. It's if you're doing null hypothesis testing and you've got a sample that's less than 0.05 probability, that's when you get to say they're statistically significantly different. That's when we get to use that term, which is, it's got a lot behind it. And this is what we've been talking about so far the whole time here. So if we say it's significantly different, if it's less than 0.05, if it's greater than 0.05, then we get to say not significant. That's what that NS usually refers to as NS not significant. Then we retain the null. Really important for you to understand this retain the null. We don't really we get to reject or retain the null. That doesn't mean we accept the null. A lot of people will say, "Ooh, we get to accept the null." No, you don't want to accept the null. If you accept it, you're accepting defeat. Don't do that. You want to reject the null typically because you believe in your alternative hypothesis, that hypothesis of difference. But if you don't get the math to support it, you don't get the statistics to support that kind of stuff, you just retain it, at least for now. Maybe you get a better sample, that kind of stuff. Okay, so if I was in class, we could probably draw this. Imagine me on the board drawing this, one of my many probability data distributions. And so you got the hump, you got the normal curve, and so the rejection region. The rejection region are the probabilities that are less than 0.05. So the probabilities that are going to be less than 0.05 are going to be the tails. And if you remember, less than 0.05, it's kind of like that 68, 95, 99 standard deviation kind of stuff, where it's 68% of the data between plus or minus 1 standard deviations, 95 between 2. So that 95 leaves kind of that 5%. So we're going to be playing around a t-value around a 2 here. So that's the rejection region. So if you're going to draw it, that region on the tails are typically what we're going to say that's our area that we get to reject. So what does that mean? That means if we find a t-value that is in that area, then we get to reject the null. And so this critical value numbers at the in your t distribution, that's going to be telling us what number we can reject. And so, all right, so let's unpack that a little bit. Depending on the size of your sample, those critical values change. So if you remember when we were talking about in class, previous classes, about how that t table in Appendix C, that t table, those values change based off your degrees of freedom. That degrees of freedom are basically that n-1, so that's your sample size. So those values will move based off your sample. So that's what I'm talking about when I talk about critical values here, is that we have to look up the critical values. And again, we'll probably go through this as an example when we come to the Doritos thing. Oh, I guess I went back. I'm sorry. So we'll go more into this example in the next PowerPoint presentation, in the second part of chapter 9. All right. Goodbye.